Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 53. It's on the enthalpy of reaction, which is the amount of energy taken in or released during a chemical reaction as bonds are broken and new bonds are formed. And look no farther than nitroglycerin for a reaction that creates a huge amount of energy. It was used by Alfred Nobel, a scientist and explosives expert, but it was highly unstable and his brother was killed in one explosion. So he invented dynamite, which essentially stabilizes nitroglycerin by wrapping it in some kind of cellulose. And so it was used not only in mining and construction, but it was also used in war, leading some people to call Alfred Nobel the merchant of death, which made him feel a little bit bad. He put all of his money into a trust and then created the Nobel Prizes, which are famous to this day. And so in the enthalpy of reaction, what we're looking at are the reactants and what are called the bond energy, the amount of energy it takes to break the bonds in the reactants, and then the amount of energy that is released in the products, which is essentially the negative bond energy. And you can think of putting these on a balance beam. And if there's more reactant energy consumed, we would call that an endothermic reaction. If there's more released, we'd call that an exothermic reaction. Now remember, these reactions sit in their surroundings, and since energy can neither be created nor destroyed, in an endothermic reaction, thermal energy is going to go from the surroundings into the reaction. That's going to cause that reaction to feel cold. And the opposite if we're looking at an exothermic reaction. Now, if we're looking at the amount of enthalpy reaction there is, Hess's law is something that kind of lays outside of what you should know in AP chemistry, but there's a few ideas that you should really be able to apply. And so if we look at an exothermic reaction like this thermite reaction, we can look at the energy of the reactants and the energy of the products, and we can see that this is a downhill reaction. In other words, we're releasing energy, and that energy is called the enthalpy of reaction. Now, it's given off from that reaction as heat into the surroundings. If we were to actually measure it, that's going to be the change in enthalpy, which is simply the enthalpy of the products minus the enthalpy of the reactants. In this case, it would be negative 850 kilojoules per mole. Now, if I were to show you an enthalpy diagram, it would simply look like this. An enthalpy diagram is different than an energy diagram in that we simply put the enthalpy of the reactants and the enthalpy of the products. Since we're subtracting the reactants from the products, in other words, since the products in this case is lower than the reactants, we're going to get a negative value, negative 850 kilojoules a mole. Now, what does that mean? Where does that energy go? It's going to go as thermal energy to the surroundings. Now, something interesting is that if we actually turn that reaction around and make the reactants the products, look what happens to the change in enthalpy. It stays the same. The only thing that changes is going to be the negative value that was in the front. And if we swap it around again, it's going to be that negative again. And so this is the first of Hess's law ideas that you should understand. That is, if we reverse the reaction, then we have to reverse the sign in that change in enthalpy. If we look at an endothermic reaction, in this case we have an uphill reaction where the products actually have more energy than the reactants. And so this is going to be our enthalpy of reaction. It's moving from the surroundings as thermal energy into that reaction itself. We could measure it and we would find that it is a positive value. Now, how do we measure that? We're going to use a calorimeter, remember. We're going to have the reaction take place surrounded by water. We can measure the change in that heat of the water and we can measure that enthalpy change. It's a positive value or an uphill reaction, and the reason why is that our products have a greater enthalpy than our reactants. Now, we don't have to know what that energy is to begin or at the end. We just have to know what that change is in order to measure enthalpy. Now, what's interesting, if we take a look at a reaction, we find that it's usually made up of a number of smaller reactions. And so in this Born-Haber cycle, what we're doing is taking lithium solid and combining it with fluorine gas, and we're making lithium fluoride. Now, if you look at that change in enthalpy, see, it's very small, and it's going to be an exothermic reaction because it's negative. But if we look at all the steps of this reaction, this would be an endothermic, this would be endothermic, this would be endothermic, and then we have two exothermics. And so this is the next of Hess's law that you should be able to apply. And that is that the enthalpy of the reaction is equal to the sum of all of the reactions that make up that reaction. So lots of times in chemistry, you'll be given a target reaction, and then you're going to have parts of that reaction. And your goal is to figure out the change in enthalpy of that whole reaction. It's pretty simple algebraically to solve this, as long as you remember those two parts of Hess's law, that if we reverse the reaction, we have to reverse the sign, and then the sum of all the parts is equal to the sum of the whole. And so if I look at this equation right up here, I've got my carbon on the left side, and so that's good, but you can see here that I have my carbon monoxide on the left side, and I eventually want it on the right side. you can see here that I have two exothermic reactions. And so the first thing that I could do is I could simply switch this reaction around. That's totally legal. Watch what happened to my delta H. My delta H now is a positive value. And so I can change the reaction around, and then I'm good to go. If you look at this, I've got carbon dioxide on the left, carbon dioxide on the right side, and so I can actually cross those off. And now I'm kind of left with almost just what I want. There's one problem here. I could move my carbon down here. I could move my carbon monoxide here. And I'm left with my oxygens. Well, on the left side, I have one O2. On the right side, I have a half of an O2. And what am I looking for? A half of O2 on the left side. So what I can do is I can simply cross that off. And now I've just got a half O2 on the left side. And so now I've totally got my reaction. All I do now is I simply add these up. So algebraically, I can add these up, and this is going to be the delta H of that whole reaction. Let's try a little bit harder one. Now you could pause the video at this point, and you could try this on your own. That'd be a good thing to do. I'll wait for you. Okay, so let's get at it. So here's our target equation right down here. And so you can see here that I have my NO on the left side, my nitrogen monoxide, and so that's good. I'm going to leave that there. But I really want is my oxygen all by itself on the left side here. So I'm going to take this and I'm going to turn this equation around. You can see that I got a negative value right here. So that helps out a little bit. You can see here that I have two ozones on the left side, and so if I could get those to cancel out, that's going to help me a little bit. So I could switch that around. So these are going to cancel, so that's good. What am I missing then? I got my nitrogen dioxide on the right side. Well, you can see here that I really want just one of these on the left side. And so what I could do is I could take that whole equation times a half. Well, if I take that whole equation times a half, watch what's going to happen to my delta H. I'm going to have to take that times a half as well. Okay, so let's see how we're doing so far. I got my ozones. I can get rid of those. Now if we get to the oxygen, this is really convenient. You'll find this is lots of times very convenient. On the right side now, I've got one O2 plus a half, so that's 3/2 of an O2, which is the same that I have on the left side. So I could cross out all my oxygens. Now I simply add that up. There's my target reaction, and now I simply add up all my delta H's, and that's going to be the overall exothermic reaction that I'm looking at. Okay, so did you learn qualitatively and quantitatively patterns in enthalpy of reaction? Again, it's simply a balancing act. We look at the energy it takes to break the reactants, the energy formed by the products, and whichever way that balance tips, it's going to tell us what kind of a reaction it is, and then we combine reactions to figure out the sum of all the parts. And I hope that was helpful.